Welcome back, everyone. It's spring 2022, and this is Introduction to Statistics. We're starting chapter 3, and chapter 3 is on numerical summaries of data. So what does that mean? What is a summary? The summary is just like wrapping up all the data. Can we say something about the data just using one value? Summary. Can we say something about the data just using one value? Or as few values as possible? Or as few as possible. So let's take a look at our four graph. Well, three. We'll go with it. Well, yeah, we'll go with three for now. The uniform graph is really unexciting and it doesn't do a whole lot. So we got our bell-shaped graph. And we talked about all these already, but it's important to know. So we have like a number line, something like that. And I'll put a skew left on the screen real quick, just to get an idea how they're different. Because skew left means the tail is longer on the left. That's about good. So one thing we could say is, well, one way to summarize it we could do is, well, where is the hump? Where's the tallest point in the graph? Well, we could look right here for the bell shape, and it's right about in the middle, right? So this is the tall point. We'll call it top for ease or shorter words here. Top is here. And the top looks like a pretty good one for the bell shape. There's about as much going that way as there is going this way, going to the left and the right. So the top looks pretty good. I like it. When we look at the skew left, though, well, there's a lot there, but this side, there's a lot more data over here than there is over here. If we add up all that stuff, there's a lot more going on to the left. So, is this good? Well, it turns out, well, where would the middle of the data sets be? Remember, this is a whole bunch of values. And like for the height thing on the project we were working on, if we had a whole bunch of people's heights listed, this top thing for bell shape is going to be right about where everyone's, the middle height, the average height, right? So in a bell shape, the top tends to be like the average. Average is right here, right at the top. But over on the skew left, like there's a lot of low values over here, way over here on the left. Not a lot, but there's enough that it's like really like you get, if you average in a 0 on your test grades, you know what I'm talking about. Or you get a 0 on an assignment, it really can drop your score. So all this is the top. The average tends to be over to the left side. And so, well, identifying the top, is it really a good choice for the center? Is the average a good choice for the center? If we look at the median or the middle, where is actually the middle? If we put everyone's height in order and we just found out what was the middle number, it turns out on skewed left graphs that the middle tends to be a little bit to the left, or I'm sorry, to the right of the average, but to the left of the top. This one tends to be like the middle or the median. And on the bell-shaped graph, it's the same. The average and the median or middle are really at about the same point. And if we look at skew right, this kind of flips the graph around. I can put these down below. Average, and I'm going to put tallies there for a second. And skew right, change the yellow. We have the long tail on the right. And even though we've got the top right here, the middle tends to be like closer to the top. And then the average is a little bit further to the right, because those high numbers now, this is like if Elon Musk is in the room and we're talking income, he's going to make the average go way up. And so the average is like way up away from the center of the peak. So when we're trying to figure out what we like, if we wanted to use center or something like that, what's the most reasonable stuff to use? It turns out we use different things for the bell shape and the skewed graphs. And so let's start talking about what those are. I've said average and I've said middle a few times. Let's just delve into that. The average or the mean. Now, in statistics, we use this symbol right there for population mean. And we use an X with a bar over it on the top for a sample mean. And if you're familiar with mean, like if we had 3 values, we would like add up the first value and the second value and third value, and then divide by 3. That's how you average stuff. You add up all the values and divide by the total number of things. That's the same thing we're going to do here when we're looking at population and these other ones, but I don't know how many values there are. So the way they put this in a notational form is they say, they put this symbol and then they say xi, where I is just for each value. So I have an x1 up here, x2, x3. It's the ith data value. Ith data point. And this symbol right here, this crazy looking E, this is sigma, capital sigma. It's a Greek letter. And it means just add the shit up, add everything up. I really need to get rid of that rainbow pen. It's fun for a second and it's just harder to read. And then I said we add everything up. It's kind of like what we did up here. We add everything up, but then we had to divide through by the number in the group. And so when we do that, when we do that for the population, we use big N. So I is for ith data value. Big N is for population size, capital big N, capital N. So if we have like we're doing COS students and there's 15,000 students, big N would be 15,000. And we would have 15,000 data points to add up. And they do this every year. They add up all the stuff to say how many people got degrees, how many people graduated, you know, all that good stuff. They like to pat themselves on the back, and it's important to know that we are doing something. We're getting people towards their goals. And they use this data as a way of tracking it. And so sample or the average is quite common. But if I wanted to do stuff like that, I would just do a sample. And sample, we have this X. And the notation is very similar. We're going to have that. We're going to have the big XI. We're still going to have the sigma thing, which means add it up. But now we're going to put it over little n. So we use little n for sample size. And we'll do an example in a second with these. Just talking about the formulas for a second. Oh, that symbol, that U looking thing. The U has got a long tail to the left of it. This is pronounced Mew, like Mewtwo from Pokemon. It's spelled Mew, M-U. It's a Greek letter. So it's got the Pokemon sound to it, Mew. It's not the letter U. It's got it because it's got that long tail. And I try to over exaggerate the length of the tail because it's really important to note the difference of it. If you put a letter U, people are going to be confused. If you have that, it makes more sense. And that's kind of how we do that. That's how we get the mean. And the mean on our graphs is where the average is. So we'll go back to that in a second. Let's talk about the median. So the median is the middle. Middle of the data. When organized from high to low. Or from low to high, I should say. And let's see, if the sample size is even, well, it might be easier to say odd first, the odd one. If n, the median, if n or big N is odd, like 1, 3, 5, 7, that kind of odd, the median is the exact middle. And if n is, we'll call that A. And if n is even, or if the population, or if the group size is even, erase. The group size is even. We take an average of the middle two. We take an average or the mean of the middle two values. And this is easier to see when we do it in a second. Give you a chance to finish writing that, and then All right, so let's just do a quick survey. I'm going to ask each of you a single question. Preferably you're honest, but you don't have to be. And I'll just go down the list of the participants I see. Giselle, how old are you? If you could either turn on your mic. There you go.
I'm 18.
And I can't hear you for some reason. Why? Oh, I got, damn it.
Wait, can you hear me now?
I had mute on. I can hear you now. How old are you?
I'm 18.
Okay, so Giselle's 18. What about you, Jorge?
Oh, sorry, I'm 19.
And Gabe? Gabe's 18. All right. So if we want to do the mean, well, let's arrange them in order first. Let's put them in order from low to high. If we do change the order to do low to high, we'll have 18, 18, and 19. Agreed? This makes it easier when there's only 3 people here to get the average. So if we want the average, finding the mean of our little sample size, we'll take each of the values and add them together, and then we'll divide by 3. If you're doing this in a calculator and you're doing it all at once, and you have a parentheses key, I recommend you use it around the top. Because if you don't, if you just type 18 plus 18 plus 19 divided by 3, the only thing that's going to get divided by the 3 is the 19. If we do this, I've got 18 and 18 is 36. Adding 19 is kind of like adding 20. If I added 20 to 36, I'd be at 56. But I'm 1 too high for 20. I need 19, so go down 1, 55. 55 over 3. And this is going to be like 18 and 2/3 or 18.67. So that's the average age. The median, which I did not give you the letter for earlier, but the median we tend to use in statistics is big M, median. Well, I've got 18, 18, and 19. If I go in 1 each direction at a time until I get to the middle value, 18 is the middle value. So the middle value is 18. That's how mean and median work. And it can be fairly easy when there's only, you know, a handful of numbers. You can just type them in the calculator, hit enter, divide by the total number of entries, hit enter, and you're good to go. In fact, it's quicker than trying to do it in Excel or StatCrunch or anything like that. Just you're doing a calculator real quick. If there's more than a handful, you're better off switching to a computer or something like that, where you can type the numbers in and then make sure you have your numbers right before you calculate the value. Because on a calculator, if you typo anything, just one thing wrong, you're going to have the wrong number. So while I'm illustrating both mean and median with an even number, I'm going to add my age to the group. How old do you guys think I am? Did I tell you guys how old I am? How do you guys think I am? Who's going to be brave? Nothing. No guesses? Cowards. Let's see. Oh, I like 35. Good guess. That's a fantastic guess, but it's wrong. I like it though. I'm born in 75, so that makes me 40. Let's see. 45, 46. I'm 46 right now. I'll be 47 in a few months. So what does adding my age to the group do, and for the mean and the median? So my new X bar will do 18 plus 18 plus 19 plus 46, now over 4. And let's see, I had 55 before, I add 46. Adding 45 would be exactly 100, so 46 would be 101 over 4, and that ends up being 25.25. And the median, so I'll go through the numbers again in order and illustrate the idea with an odd number like this. So I go in one from both sides. I get to these two. These two are the middle numbers. I take an average of these two numbers. 18 plus 19 divided by 2 is 18.5. So that's the idea of doing it with an even number of people versus an odd number of people. And this also points out something important. Did adding me to the group change any of these a lot? Tell me what you mean, Gabe. Give you a second to type it out and I'll read it out. It changed the mean by a little more than 7, right? The mean changed by actually, well, yeah, pretty close to 7, right? What about the median? You think that's a big change in the median? No. So adding me, I am an outlier in the age group right now for our little sample. Based on age. And it had a huge impact, like, because 7's like almost half, right? 9 would be half. So going 7 is almost half. It had a big impact on the mean, but very little impact on the median. And when we have a summary statistic that is affected by outliers versus one that's not affected by outliers, summary stats that are not affected by outliers, like the median, which are not affected by outliers, we say the statistic is resistant. So the median is resistant to change, or is resistant to outliers. The mean is not resistant. And so that idea actually helps us choose what we want to use to count as like our center for a data set. This motivates the choice for a center. I don't know that I hit record. Oh, good, I did hit record. This motivates the choice for the center of the data set. For a bell-shaped graph, where it's right there in the middle, we're going to use mu or x bar for our center. And for skewed graphs, we will use the median. Now, I thought I should point out in social sciences, big M tends to be used for mean in social sciences. And maybe I should make that look more like an M than a funky U. In social sciences, big M is mean, but not here. But not in stats. If I could change the rules, I would. That seems kind of foolish. You know what I mean? For the skewed graphs, one way to remember how the mean and the median look, well, let's do this again. On a bell curve, bell-shaped graphs, the mean is approximately equal to the median. They're pretty close in value, so either one technically tends to be good. On skewed graphs, the median is closer to the hump. Than the mean. Let's see, is the mean resistance? No, the mean it just isn't resistant. Resistance implies when you're adding new values, if the new value is drastically different, either way too low or way too high, it's going to affect the value of the mean. The only time well, even if I interviewed 1,000 people from COS and figured out everyone's annual income, and we did the average annual income. Even if I included professors and students and stuff like that, so there's a range there. If we go and get Jeff Bezos or Elon Musk or someone like that, add their income, just adding a single one more person, 1,001 people, they make so much money that the mean is no longer relevant. Like the average will say we all make, $1 million, which is completely unrealistic, even for professors. It's too bad. That would be great. I would love to make $1 million. So the mean is just not resistant, which it isn't a problem. But it just needs to be noted. We will do all this in StatCrunch in a second. But there is one more thing that we use as a center. Both the mean and median are numerical. values. They're related to numbers. What about for categorical data like hair color? For categorical data or qualitative data, back to that word again, qualitative data, there is no number to average or way of doing a median. Find the median or mean. In this case, we use something called the mode. The mode is the most common response. Or the response with the highest frequency. In our age comparison that we just did, there was 2 18s, 1 19, and 1 46. So for our age group or our age sample, the mode was 18. So we can use mode for numbers. We can definitely use mode for numbers, but it's the only thing we can use for things like hair color or, favorite music group or whatever kind of question you have that does not have a numerical response. And even where like a numerical response, like finding the average doesn't make sense. Like finding the average of zip codes, even though they're all numbers, it just doesn't make sense. It's foolish. So definitely mode is the multi-purpose. And even though like the mean and the median are the same for bell graphs, and the median is the method of choice for skewed because it's closer to the hump, we tend to still use mean for the bell graph because we use mean in a lot of other calculations. So let's go take a look at StatCrunch real quick. And we'll talk about how to do it there. So I got my screen up. Move that out of the way a little bit. I'm going to delete this top row. What is it? Row select. Oh, nope. Just edit. Row, there we go. Edit row, delete. All right. So we got these ages in here. I could sort them. You can actually sort them just by clicking on that little down arrow and going sort table ascending, which is pretty nice. And I could scroll down and find the median, like how many entries are there? There's 182 entries, which is even. So half of 182 is 91. So we'd want like the 91 and 92, take those two entries and average them. 91 is 22 and 92 is 22. Since they're the same, the average is 22. The median should be 22 when we calculate it. But let's just get to the calculating. I definitely don't want to do that mean by hand, right? There's 182 numbers. Fuck all that. That's just punishment. So if we click on stat at the top and then we choose summary stats, we're going to choose column. Almost all data generally that we use is sorted by columns. Very rarely do we sort data by rows. We just write things downwards as a people. That's just what we do. So summary stats columns. And you can go through and select the column you want to use. We'll look at the age one. So I'm going to click on age one. And then the statistics ones, the values in this right box right here are all the ones they're going to show. These are the default ones that they show. They show N, the sample size. They show mean, variance, and standard deviation, which we'll cover in just a bit. Standard error is very close to standard deviation. It's got the median we just talked about. We're going to do range. Min is the lowest value, max is the largest value. We'll do Q1 and Q3 on Wednesday. These are all values you commonly use. Or if you just want to choose one of them, you can click on it and then it clears everything else. If I try to add median as well, and I just click on median, it's going to replace it. So I can scroll up and down, and when one of them's clicked, I hold down Control and click on another one, and it'll put it up there. And I'm going to look for the mode too. Mode's at the bottom. I scroll down without holding on Control, click it and add it, and we'll just look at those three real quick. And we've got median that we calculated, 22, just like I said, between 91 and 92. The mean age is 27.5. And mode, there's multiple modes. So there's a little bit more to say about, does it say what it is? Yeah, so there must be, we could figure it out if we wanted to do a frequency chart. No, I do not want to turn on binning. 18 and 19 both have 24 people in it. And so that's why it's saying there's multiple modes. So it's really easy. We did stats, summary stats, columns. And I'll write this down on the notes in a second. Then we choose our column and we choose what statistics we want to show. If you want to store your results in the data table, check what happens when I click store in the data table. And I'll just do mean and median real quick. If I click store in data table, oh, I didn't tell it where the age is. Tell it where the age is. It says new column added to the data table, and it added it right here. It said what we're talking about is the age, the mean, it says above it at the top, mean 27.5, median is 22. This can be handy if you're trying to get a bunch of stuff stored in a table. So just a good thing to know. I think it's even available with the frequency. It is. You can store the frequency in a data table as well. I do not want to turn on binning. So it stores the results over there. So oftentimes when you get results, if you want to store them, you can get it stored into the screen. Let's go take a look at the further the notes a little bit. So in StatCrunch, you're going to choose stats, summary stats, and then columns. That's step A, that's getting to the right area. B, select which columns you want to look at. C, select the summary stats that you want in the stat box. And then D, hit compute. Compute button. I would say at the bottom, but I've seen people using it on their phone and it computes at the top. I really don't recommend using this on a phone if you can avoid it. And as we saw when we did the mode in the age thing, if there's two modes, it should have said it here, but it didn't. If there's two modes, we call it bimodal. And more than two is multimodal. Any questions? Take a short 2-minute break or a 5-minute break if you want. We're going to do another section, but it will be done before 4, I believe. Well, I know we'll be done before 4. But go ahead and take a 5-minute break real quick. I'll pause the recording. Okay, I'm going to start putting up some numbers in case people are still coming back. We're looking at the next section now. This is 3.2. And before I give away the name, let's just look at 2 groups. I'm going to have group A and group B. Group A has the numbers 46, 48, 50, 52, and 54. Group B has 10, 30, 50, 70, and 90. And to give you guys some practice with the mean, calculate the mean of these 2 groups real quick. And median. Let's do mean and median of these 2 groups. Anyone have an answer? Right there. Oh, come on, you guys.
Would the medium for both group A and B will be 50?
The median for both groups A and B would be 50. That's correct. Median for A is the same as the median for B, which is 50. What about the mean? Oh, Giselle left. It's like, oh, hell no, I ain't doing no math in class. It's 50 as well, right? Thanks, Gabe. So X bar for A and X bar for B is both 50. So all of our measures for center get the same answer, right? Does that paint the whole picture? If these were test grades, what would this say about the class or the students that I sampled? Well, group A, everyone failed, right? Out of if 100% say it's 70% or higher is passing. At group A, everyone failed. Group B, 2 people passed and someone got an A. So clearly this measure for central, the mean, median, and mode, I should have said this in 3.1. They're called measures of central tendency, how we tend towards the center. Our measures of central tendency don't show everything. Group A is all bunched up. Is a close group, close in value group. While in B, the values are far apart. And if I did this on a number line, if I did a number line and I put 50 in the middle, and let's see, let's do 30 and 10, 70 and 90. Group A is like right here. Group A. But group B is all over the place, isn't it? We got one over here, one over here, one there, one there, one there. B is kind of spread out. Whereas A is not spread out. So we use more than just the mean or the median to discuss things. What we use to describe this spread or this dispersion, that's our one of our new words. Although you really don't see it in a lot of, it doesn't show up much past this chapter. Dispersion is a measure of how spread out the data is. Is a measure of how spread out the data is. or how much it deviates from the center. One of the things we use for dispersion is called the range. This showed up in our summary stats thing. Summary stats, one of the options was range. Range is the highest value minus the lowest value. For group A, our highest was 54 and our lowest was 46. And that gives us a range of 8. For B, we had 90 minus 10. That gives us a range of 80. So that kind of tells that range is something we use to show how much something is spread out. Again, that's not really enough. Like if we're talking about, grains of sand on the beach, 80 and 8 really isn't a big difference. That's not a big number. But if we're talking about the number of passing students in a class, assuming class sizes are that high, it's huge. Is this resistant to outliers? Is range resistant to outliers? Well, we can check, right? It's not. It's not resistant. That's correct. Why? Well, it's rather not why, rather than trying to put words to the why, it's kind of easier to show. Let's add 100 to group A. And now the range of A, our new A, is 100 minus 46, which is 54. So having a number that's far different from the rest changes the range by quite a bit. So the range is not resistant. So range is, that only tells us stuff about the highest and lowest value. This is where we get into something you've probably all heard the words for before, whether you've been taught the stuff or not. Standard deviation. And sometimes it's just called deviation. By lazy folks like me. And it's important to know this is for bell-shaped only. Bell-shaped only, shape only. Is this really reliable? And we'll show what you can use for like non-bell shape today as well. But the more skewed it is, the less the standard deviation is like a good measure of what we're doing here. So let's just go over what the symbols are and how they differ between population. Let's do population first. I'll do population first. So for population standard deviation, we use this, which is looks like a large or a little O with a tail on it. This is lowercase sigma. Or the big E was uppercase sigma. I don't know why the letters are so drastically different looking. Lowercase and big case sigma, or lowercase and uppercase sigma look drastically different. But that's what we use for population. And what we're going to do is it's easier to kind of walk through it. We take the sum of a bunch of stuff. What we do is for each data point, we take the data point and we subtract the mean. Then we square that value. And that's what we add up. We add up all of these. So do all the subtractions, square each subtraction individually, add them up, then divide by n. So that's sigma lowercase. And it looks like we need to know some things to do all this. We need all the data. Xi is all the individual data points. We need all the individual data. And from that, we can kind of get the rest. N is the population size, but we could just add up all the data we have to get N. And then once we have N, we could find the mean, mu. So that's population standard deviation. And in StatCrunch, it's called unadjusted, shit, misspelled it already. It says UNADJ period STD period DEV period. In the summary stats, in the stats, summary stats column. And we'll look at that again in a second. But we need to talk about sample standard deviation because it's slightly different. It's almost entirely the same except for a single difference. So for standard deviation for a sample, we get really, really clever and we use S because that's how we roll. We're like, fuck it. S is for standard deviation. S here, very similar. We're doing the sum of all the data points minus the average, which is the X bar. We're squaring those. And then we're dividing by n minus 1. And I completely missed something. I got to put on the other one. Divide by n minus 1 and then take the square root. I missed that up top. Divide by the square root. Okay. So how does that work for us? Why is there a difference? Why is there a big N? Why do we use the population size for population standard deviation and only n minus 1 for a sample? This n minus 1 is called the degrees of freedom. And here's a real quick example of how degrees of freedom work. Let's say I have 3 ice cream cones, chocolate, strawberry, and vanilla. Jorge, do you like chocolate, strawberry, or vanilla? Which one would you like if I had ice cream to give you right now?
I'll probably choose strawberry.
You like strawberry. All right, Gabe, I'll give you the next choice. Strawberry's gone, so you could choose between chocolate or vanilla. Which would you choose? Chocolate. So I get the final one. Vanilla's left. Do I have a choice?
No.
Not really. That's where the kind of like the idea of the n-1 shows up. They found that when they're doing a sample, they put it in there, it compensates for the lack of choice in the final thing. It acts like a forcing thing to get it to work. The final one is picked for it. It's a little complicated, but that's kind of like how it works. It's a big difference. All these things mean the same thing. We're going to take each individual data value. We're going to subtract its average. We're going to square it. We're going to add them up. And then we're going to divide by something related to the size of the group. The only difference is this one for sample is n-1, and it's big N for the total population for population. And in StatCrunch, this is just your regular. This just says standard deviation, STD DEV. That is the one most commonly used, and so that's why it gets that. And the unadjusted one is for the population because there's no adjustments made. The subtraction of 1 is an adjustment. And we'll find, you'll find that this kind of measures the spread out. And we can just show it with our ages. I'm going to change my age to 25 real quick for the purpose of our 45 for the purposes of our groups. We had 18, 18, 19, and I'm going to say 45 just because the number works a little bit easier. This adds up to 100. Divide by 4, the average is 25 exactly. So if I wanted to do, I'll show you doing a little bit of this by hand. If I wanted to do this by hand, I need each of our XIs. So XI is 18, 18, 19, and 45. Then I'll do the subtraction. XI minus X bar. 18 minus 25 is -7. We've got -7 there. 19 minus 25 is -6. And 45 minus 25 is 20. If I then square each of these, I get the signs go away. Whether it's negative or positive goes away. Then if I add them up, so we'll add 49 and 49 is almost 50 and 50 is like 98. So 498 and then 498. If I take away 2 from this, I'd get 500 and I'd have 34 left, 534. Then I would divide by n-1. There, n was 4. There was 4 of us in the group. We're just a sample of the ages at COS. So n-1 is 3. So we've got 534 divided by 3 is actually evenly divisible. It's, let's see, 1, 23 is a 7, and then 3, 178. Quick fun fact, if you didn't know this, to see if a number is evenly divisible by 3, add up the individual digits. 5 plus 3 plus 4 is 12. 12 is evenly divisible by 3, and that means the big number is evenly divisible by 3. That's crazy, but it works. It's like some math magic. Finally, the square root of 178. that one I'm not doing in my head. 169 is 13, so it's like 13 something. Square root of 178. 13.34. So even with just 4 entries, this was quite a bit of work, right? This is a pain in the ass to do by hand. It took a while just to do for 4. And the only reason I did it for 4, rather than saying, go watch a little 5-minute video on online about it, is because I can do it in 4 in a reasonable amount of time. This sucks in the big picture by hand. Don't do this by hand. Avoid doing by hand at all costs. But I think one of the homework problems makes you do it for a small data set like this with like 5 numbers, just so you can do the struggle and so you can appreciate how much the computer helps you. Avoid doing by hand at all costs. And the reason why is not just the time, but anywhere I make a mistake in there, anywhere I make a mistake, it's gonna show up in the end. The error gets compounded. The more errors along the way, the more the answer's off. And if you've got like 100 of these, there's a good chance you'll have at least a couple errors by hand, and your answer is unreliable. But in StatCrunch, we can do this pretty well. Oh, it's still on eraser, but that's why. And we talked about this a second ago. I said it a second ago. In StatCrunch, we're just going to stats, summary stats, and then columns. And then std dev for samples. I wish they'd chosen a different abbreviation than std, because that means something entirely different to most people. And then unadjusted UNADJ standard deviation is for populations. Again, the symbols are for sample is S, for population it's sigma. And these are related to something called variance. Variance is just standard deviation squared. So we've got S squared or sigma squared. And you will find, in fact, let's look at that chart real quick and I can point it out. If I didn't add my age to the group, that 45, we wouldn't have this 400 in the sum, right? We wouldn't have the 400 in the sum. I could add those up and I'd have 49 plus 49 plus 49. I'm sorry, plus 46, 36, try again, is 134. If I divide, well, shit, I could have just subtracted 400. That was me being lame by doing it by hand. If I add that up without my age in there, the answer divided by 3 is 44.6. And the square root of that answer is 6.68. So without me, without me, this value ends up being 6.68. And so it's clearly affected by outliers, which makes sense. The mean was affected by outliers. And since standard deviation uses the mean, that is a W/O for without. None of this standard deviation and variance is not resistant to outliers. And you'll notice that when my age was in there, we had 13.34. And when my age is out, it's 6.68. Outliers make these values go up. Both negative or both low end outliers or high end outliers. So outliers cause these values to rise. Not just outliers, just a bigger spread apart. A wider range does the same thing. So kind of like the greater the deviation, the greater this number is, the more spread out the data is. Give you a second to finish that. I'll hop back over to StatCrunch, show you the use of this. Then we'll talk about for non-bell-shaped graphs. Yeah, I thought the number by itself isn't helpful, but maybe seeing it up there when you actually compare the ideas, like my age is in there, it's bigger. Without my age in there, it's smaller. It kind of gives you a measure of how spread out the data is. And when it's more spread out data is called less consistent. And the idea behind that is if you had like raffle tickets and all these numbers on there, reaching into a bag for group A, you're going to get a number pretty close to 50. It doesn't matter what you pick. Even the 46 ticket is pretty close to a 50. Reaching into group B and grabbing a ticket out of there, you could end up with a 10 or a 90, which is nowhere near 50. So it's not, you're not consistently getting near the mean when you pick values at random from it. That's the idea of less consistent. Let's hop on over to StatCrunch. Does anyone need this up on the screen longer? There's only 2 of you right now, so.
I'm good.
All right, Gabe, you good? Yeah, all right, so. Not all that exciting. I mean, we're not gonna do anything drastically different. I'm gonna go, we'll do the same thing for age again. Stats, summary stats, columns. We'll click on age. And standard deviation and variance are there, or both samples. I wanted to just point out real quick what the other ones were. Unadjusted variance, unadjusted standard deviation, they're way down at the bottom. They're not automatically selected because rarely do you have an entire population worth of data. Almost always this stuff is being done with the sample size or sample group. You just click compute and we get the standard deviation and the variance. And one is the square of the other. And how does standard error look on this list also? The hell is standard error? I gotta look that up. I don't know what that is. Let's see. And you will use mean and standard deviation a lot. A lot of the stuff at the end of the semester relies heavily on the mean, heavily on the standard deviation, and several of the hypothesis test methods use variance, especially if you take like an upper division stats course. This is just an introduction to stats, and some of us do it, some of us don't. I tend to focus on the mean and standard deviation ones, less on the variance. Let's go back to the writing pad. So for skewed groups, or skewed data sets, don't know why I put the apostrophe there. For skewed data sets, we use, and I love this name. This is one of my favorite names in the whole world. I'm going to write it down. That's the guy's name. It's pronounced Chebyshev. We use Chebyshev's inequality. And Chebyshev's inequality is if we're talking about k deviations for k deviations from the center. One minus 1 over k squared times 100% of the data is captured. And k has to be greater than 1. If k equals 1, I've got 1 minus 1 over 1 is 0, 0%. But doesn't hold true for a lot of it. And I think this needs a picture. So I'm going to do the bell-shaped picture first. I think the bell-shaped picture is the most useful because it's the one you're going to see the most this semester. Just pretend that's a little bit centered better. Let's add a little bit more of that. Right, there we go. So we've got the mean in the middle. And I go out. If I add 1 deviation to the mean, 1 standard deviation, we're just adding numbers here. Add 1 to the mean, I go to the right a little bit. And if I add 2 standard deviations to the mean, I go a little bit further to the right. And if I add 3 standard deviations, I go a little bit further to the right. And this is about right for what I'm picturing right here for a regular bell curve. If I subtract 1, I've got mu minus 1 deviation. I could do subtract 2 deviations. And subtract 3 is over there. You generally don't have much more than 3 deviations either direction. And before I apply the Chebyshevs, I'm just going to tell you what the percentages are for standard bell curve. Between mu and 1 deviation away, this has got about 34% of the responses. So if we had like 100 responses, there would be 34 answers that make up this group. And that's 34 in either direction. The next group over is 13.5 in either direction. And these again are percents. If I do these groups right here, I've got 2.35%, the third deviation over. This is the percentage of data that's in that group. You will want to memorize this table. I'm going to do it again on Wednesday, and I'll probably do it a couple more times this semester. But I'll show you where to find it in the file section a little bit too. Beyond that is 0.15% of the data. And so for bell curves, if I just do 1% or 1 deviation either way, if I do mu plus or minus 1 deviation, 34 and 34 is 68%. Oops. %68% is within 1 deviation. And I'll tidy this up a little bit, make it, because I got a lot of writing in the way. If I go out 2, and if I add up all those numbers between -2 sigma less than x less than, I'm sorry, mu minus 2 sigma, and then mu plus 2 sigma, adding in the 13.5 and 13.5 takes this up to 95%. And this is mu plus or minus 2 deviations. If I do 3 deviations, mu plus or minus 3 deviations, which is mu minus 3 sigma, is less than whatever our data value is, xi, is less than mu plus 3 sigma. This is 99.7%. So this is called the empirical rule. I'm just misspelling that. IRICAL. The approximate percentages they count them as they say 68% within 1 deviation, 95% within 2 deviations, 99.7% within 3 deviations. So this is plus or minus 1 sigma, plus or minus 2 sigma, plus or minus 3 sigma. And the reason why those numbers are approximate, if you actually do where you capture within 2 standard deviations for a good sized data set, it's more like 95.3 or 95.4. But 90, it's so close to 95 that it makes a good rule for later on for determining if something is unusual or not. We say that further than 2 deviations from the mean or center is unusual. You will see, you will be asked repeatedly this semester, is this unusual or not? And since it's outside of the 95% range, it's the outmost 5%. Or 0.05 is unusual. And that 0.05 is going to come up a lot in the later part of the semester. How Chebyshev works. Let me pause and give you a second. So we said for bell curve, 2 deviations was 95%. Let's look at Chebyshev's version. He had 1 minus 1 over k squared times the percentage. So if I do k equals 2 to represent 2 deviations, I have 1 minus 1 over 2 squared, which is 1 minus 1 over 4, which is 0.75. And when I multiply that by 100 to get percentage, I get 75%. So it's less. Chebyshev's inequality captures less data, but it's more realistic for skewed data. I don't know that there's any problems in the homework that have it, but there might be one. So I thought I'd better walk you through a calculation and show how it goes. In terms of memorizing those numbers, because I said you're going to want to memorize that graph. Oh, back. No, stop. What the hell's going on? You. There we go. Oh, draw. I want draw. So in terms of those numbers, remember, I memorize the 68%, 95%, and 97%, 99.7%. And from that, I can get all the other numbers, like those percentages on the charts. 68 is for 2 different regions, the +1 or -1. 68 divided by 2 is 34. And then for the next two out, I have 95 minus the 68 to represent the next two out. That's 27. And if I divide 27 by 2, I get 13.5. And then if I do in the 2 to 3 deviation range, well, that's going from 99.7% to 95%. 99.7 minus 95 is 4.7. Oops, 4.7. If I divide that by 2, I get the 2.35%. And everything outside of it, well, it's all got to add up to 100. So 100% minus 99.7% is 0.3. And divide that by 2, and I get 0.15%. they will ask you in several problems. I'm going to go back up to, I'll let you write that down. I'll go back up to the problems. And go back up to the chart real quick. What happened to my chart? There it goes. What the? All right, now you're starting to piss me off. So they might ask you like, and they'll do it by numbers. They won't say within the deviations. Actually, let me show you what the IQ test. Let me go back to the bottom and do the IQ test value real quick. So the IQ test, the traditional IQ test, you can actually take it if you wanted to. The IQ test is at Stanford, Binet, it's a T, test.com. This is your standard IQ test. And it's more of a measure of how good you are with math and words. Math, words, and memory and reasoning. For the population, the average intelligence is 100, and the standard deviation is 15. That's for the population. So if we put that on a bell curve, I'll put 100 in the center. And then I'm going to add 15 3 times going to the right. 100 plus 15 is 115. 115 plus 15 is 130. 130 plus 15 is 145. If I do that going downwards, I've got 85, 70, and 55. And as a reminder, these percentages are, there's 34% there, 34% here. We've got, let me just draw these little dash lines going down. We've got 13.5 in each of the next two outward, 2.35 in the next two outward, and finally 0.15 outside of that. So I'll put the 100 down there. And they'll ask you some shit like this. So here's a sample question. Actually, I'll wait a second if you're writing that down. So say something like this. What percentage of the data, what percentage of people have an IQ between 85 and 130? Why do I not have more room to write? Is like this the end of the paper? What the fuck? Huh. I'm gonna have to figure this out. And so they'll tell you, and it may not be IQ, but they'll tell you the mean is 100. They'll tell you what the standard deviation is. They might give you different values. But your idea, your goal is to like figure out how many deviations these are away so that you can draw this chart and like get a percentages. So our group is going to have, it's between here and here, 34% plus 34% plus 13.5% is 71.5%. That's the kind of questions they'll ask. I think we'll call that a wrap for today. Oh, let me show you where that chart is in Canvas real quick. So I'm going to share screen unless anyone needs that up longer. We'll come over to COS. And I'm going to pick one of the stats groups. I have 3 stats classes, but they all are set up the same. You go into files and you go into useful handouts and stats. It's in stats, formulas, and tables. Come on, load. In fact, you can see the formulas for population mean, sample mean stuff right here. Standard deviation, stuff like that. It talks about the empirical rule right here. And we'll come down and there should be a chart picture of it down at the bottom. I thought there was. Did I miss it? They changed it. It used to be in here. So one way you can see it real quick is just Google empirical rule. And they show it right there. That's not a very good graph. I'm going to go back and click on images. There we go. That's better. We're going to do Z values on Wednesday. It says Z values here. Z values are this week. It's called the Z score. But it's got percentages here. It shows them all. It says 2.5. They're covering everything outside of it. Maybe that's not a good one. That only shows 3. Jesus, they got rounding there. That's crappy too. There we go. Oh, black screen doesn't show up very well. But it's there. You can see it. The point is you can Google it. All right. That's it for today. I will catch you guys on Wednesday.
All right, have a good day.
You too. Stay out of trouble, guys. Well, don't do anything I wouldn't do.